Welcome to the 6th lecture of modern construction materials. Today we are going to talk about surface properties. We have been looking at the structure of materials starting from chemical bonding to the different phases that form within the material during solidification. Now we look at some of the properties that are related to the surfaces of the materials. Surfaces are areas of abnormality in relation to the structure that they bound. That if you remember, when we talked about defects, we said that grain boundaries were surface defects. Now the surface of a body is also a similar defect in the sense that there is no continuity of the material beyond the surface, and at the surface what we find is the atoms or particles or ions are not bounded on all sides. So they have asymmetric bonding forces only from within the bulk of the material and not outside the material itself. So that is why we say that the bonding forces are asymmetric. Also, what is important to understand or realize is that surfaces are the only part of the material accessible to chemical change, because you can have attack from outside. Chemicals from outside can access the material, can start entering the material through the surface. When we have materials that are made up of several particles, the surface area depends on the size and shape of the particles, that is, the ratio of the surface area to the total mass depends on the size and shape of the particles. So if we have smaller particles instead of larger ones, we will have a higher specific surface area. If we have angular particles, flaky particles instead of rounder ones, again you will have a higher specific surface area. If we look at the Condon-Morse diagram and see what modification we will have to make to understand what happens on the surface, you see here the dashed line which now corresponds to the surface atoms. The dark line corresponds to the Condon-Morse diagram that we have been looking at until now, where we have a curve giving us the resultant between the attractive and the repulsive forces, with this point being the point where we have the least potential energy, which corresponds to a stable interatomic or interparticle distance r sub 0. Now this is for an atom or a particle within the material when it is bounded on all sides by particles around it. Now on the surface you have an asymmetric bonding, and therefore the energy diagram is modified into this dashed line, and instead of the energy level being at this point, for the same interparticle distance now we are here. The energy level is much higher than the minimum energy level, because we have removed some part of the material, or some part of the material above this particular atom that we are discussing is missing. So this difference is called the surface energy. This additional energy that we have above the minimum is called the surface energy. Now we know that the material will try to decrease its energy to reach a stable value. In a solid, the spacing here is fixed because the atoms or particles do not have much mobility. So at this surface we realize that the surface energy will be higher by this amount, and there could be surface phenomena which will occur to decrease the energy to this point. Now in a liquid, however, what will happen is that there is greater mobility of the atoms, the surface deforms to reach an equilibrium distance which has a lower energy than this. So in a liquid we reach equilibrium on the original Condon-Morse diagram or the bulk Condon-Morse diagram, with the distance now being r prime sub 0 instead of r 0. The interparticle distance is now larger. This means that on the surface of a liquid, the distance between atoms and particles is larger than within the bulk of the material. So, suppose we take a spherical droplet of any fluid, we will find that inside there will be compressive forces and on the surface we will have tensile forces, because there has been a change of the interparticle distance on the surface. The interparticle distance now is larger, so the surface is stretched. There are tensile forces induced by this change in the particle distance on the surface. This tension on the surface induces compression within to balance out the stresses. So, that is what we see here, and on the surface we have a higher interparticle distance r prime sub 0, which is more than r 0, which is inside the bulk, and this arises because of the asymmetry of the bonding forces that are around any particular particle or atom. You see here that in the bulk there are atoms all around, so the bonding forces are symmetric, whereas on the surface we do not have this part. So, there is a part missing of the material, and therefore the energy now is higher above the minimum, and to accommodate this in a liquid, the interparticle distance increases, inducing surface tension. So, as I said, the extra energy, the excess energy above the minimum potential energy that is there in the bulk of the material is called surface energy. In liquids, the structure has mobility, the atoms are more free to move than in a solid. So, the individual atoms respond to this higher energy, the atoms act to reduce the surface area and therefore lower the energy. This reduction in the surface area, this stretching that is induced, results in what is called surface tension. Surface tension acts along the plane of the surface or any interface, and it has the units of force per unit length, say Newton per meter. For example, we can look at the surface tension of water, which is 0.073 Newton per meter at 20 degrees centigrade. Surface tension is temperature dependent, and we see in water that at 60 degrees we have a lower surface tension. So, surface tension generally decreases as the temperature increases. Now, in a solid we saw that there is less mobility on the surface, therefore, the energy at the surface is much higher than in an equivalent liquid, because the equilibrium interatomic space is not achieved and we have a higher surface energy. This higher surface energy makes solid surfaces prone to combine with chemicals from the atmosphere and attack by these chemicals, which leads to phenomena such as corrosion. Now, in a liquid solid interface we have a phenomena called wetting. This wetting behavior depends on three surface tensions. These three surface tensions are related to three interfaces: the liquid solid interface. If we see the diagram at the bottom, we have a solid surface, and on top of that, say we have a droplet of liquid. So, we have a liquid solid interface, and the surface tension here is given by gamma Ls. Then we have an interface between the vapor and the liquid. So, there is a surface tension between the liquid and vapor given by gamma Lv. Then we have a dry interface where we have the solid vapor interface represented by the surface tension gamma SV. This quantity, which is the difference between gamma SV, the solid vapor surface tension, and the sum of the liquid solid surface tension and the liquid vapor in surface tension, is called the spreading force. So if this value given here is positive, then the liquid spreads out. If it is very small, negative, then instead of spreading we have a droplet. So here we have these different cases. When gamma SV minus the sum of gamma LS and gamma LV is positive, that means the spreading force is high, then we have theta, which is the angle of wetting, equal to 0. So a surface is completely wet, complete wetting of the solid surface occurs. Here the energy of the system is now lowered when there is wetting, that is the dry surface, the solid vapor interface is now replaced by a solid liquid plus a liquid vapor interface. This lowers the energy of the system. On the other hand, we can have cases where gamma SV is less than the sum of gamma LS plus gamma LV, that is this term becomes negative. In this case theta is greater than 0, partial or no wetting occurs. Partial wetting where you have a droplet like in the middle figure, or you can have no wetting and the droplet being almost spherical. So in both cases what we understand is that the system tries to lower the energy, and depending on the values of the surface tensions you can have complete wetting, partial wetting, or no wetting at all, which is the case of hydrophobic situation. Complete wetting will be in a hydrophilic situation. So you see some examples here of partial wetting. On the left theta is more than 0, and in this case you have a droplet forming. You can have a case where theta more than 90 degrees leading to a water repellent surface or a hydrophobic surface, where you find the droplet now tends to become more and more spherical. It can even become completely spherical in the case of a superhydrophobic surface, which is completely repelling the water and the water becomes a spherical droplet. An example of this type of superhydrophobic surface is that of lotus leaves, which are known for superhydrophobicity. The texture of the lotus leaves and many other aquatic plants is such that they have several levels of micro and nanoscale structures. There is a hierarchy of micro and nanoscale structures which leads to water droplets not wetting the leaf surface but rolling off the leaf, and when they roll off they leave the surface dry and also carry away dust particles. And if you see in some of these pictures you will see that the droplets are almost spherical, like we saw in the diagram before. Now some researchers have tried to mimic this superhydrophobic surface that we see in nature in lotus leaves and so on by using polymers. Researchers in China and France have replicated the surface of a lotus leaf with a polymer called polydimethylsiloxane or PDMS and created a synthetic mimic that can self clean and be water resistant, that is there is no wetting of the surface and the water rolls off taking away dirt and dust. And this could have applications in coatings and where we want to reduce friction in micro surfaces. This is a picture showing at the top the lotus leaf, and you see the texture here it is not a smooth texture, but in the micro scale we see these small ridges and small humps, and this is at the bottom is the synthetic surface which has the same hydrophobic behavior which you see in the figures here. Here you see a water droplet that is almost spherical, and same here. So there is lot of research going on to create super hydrophobic surfaces mimicking what we see in nature in leaves such as that of the lotus plant. Now we talked about hydrophobic surfaces. We can have cases where we want complete hydrophilicity, that is we want complete wetting, that is in the case of adhesives. When we use a glue or a solder, we want this material to spread and thoroughly wet the solid surface. There should be complete wetting. With a drop of glue or a drop of solder, we want a good wetting of the solid surface so that there is good bonding. We do not want droplets forming, but we want uniform wetting. And we can also imagine that how the adhesive works is by creating a liquid solid interface, and in order to break that we need to expend a lot of energy. If we think of the adhesive as a viscous liquid, to break that bond between the adhesive and the solid, we have to create a liquid vapor and a solid vapor interface instead of just a liquid solid interface on the equivalent area. So this requires some energy, and that is why we need to expend a force to break what has been adhered or an adhesive made joint. Surface tension is also the cause of adhesion between two surfaces separated by a thin film of liquid. When you have two plates or two solid surfaces separated by a very thin film of liquid, we find that surface tension bonds the two surfaces together, and it requires a lot of energy to separate them. A good example that you might have come across is when you have two cups or two glasses, one inside the other, and it so happens that the surface between them or the interface is wet, and it is always difficult to separate the two glasses because of this surface tension of the water or any other liquid bonding the two together. We also know from this explanation that when we have to use an adhesive such as a cyanoacrylate, one of these quick glues, we have to produce a thin surface of adhesive. The adhesive layer should not be very thick. The thinner the layer of adhesive, better is the bond, because then the surface forces are larger. Now there are materials which modify the surface tension. Surfactants are compounds that adsorb preferentially at the interfaces, that is they have a tendency to be adsorbed on the interfaces and they lower the surface tension. Some simple surfactant molecules are given in this diagram taken from Young et al, and these are polar molecules with a hydrophilic end and a hydrophobic end. The hydrophilic end sticks out into water and changes how the surface now behaves. If we consider a liquid-liquid interface, the surfactant molecules align themselves with the hydrophilic end in water, and this sort of alignment lowers the interfacial energy and it results in an emulsion like we have here. If we have two liquids, a non-polar liquid and a polar liquid, they will not readily mix and they will separate when they are mixed together. But when we have an emulsion, we need the two liquids to form a uniform mix, and in that case the surfactant comes in handy and you can create an emulsion. In civil engineering we use a lot of emulsions. One that comes to mind very easily is that of paints. Lot of paints that are used are emulsions. Now surfactants are also used to create foams. In this case what happens is the surfactant molecules act on the liquid air interface. We have the liquid here and these surfactants now attach themselves to the surface and create the possibility of having foams, so that the air inside the water remains in a stable manner. So we have a foam, and foams again are used a lot in civil engineering. For insulation we use polyurethane foams. We even have foamed concrete where there are air bubbles which are stabilized within the cement matrix to reduce the density or to improve the thermal properties. At solid liquid and solid air interfaces, the molecules of surfactants can increase wetting and deflocculation. In some cases we can have the surfactant creating better wetting, make the surface more hydrophilic, that is instead of droplets forming you have water or any other liquid spreading over the surface to improve the wetting. An example of this is what we have in self cleaning glasses. In self cleaning glasses the surface is modified such that water coming from rain forms a uniform film on the surface, that is there is complete wetting, and as this water runs down the glass it carries away dirt and dust and leaving the glass clean. That is an example where we want wetting to occur and we want a hydrophilic surface. Now in lot of cases we want the surface to be hydrophobic or we want deflocculation, that is we want separation. We do not want the adjacent surfaces to bond or stick to each other. An example that again comes to mind is what happens in the case of a plasticizer or a super plasticizer. When we add it to concrete, the polymers bond to the surface of the cement particles and ensure that the cement particles do not flock together or stick together, do not agglomerate. This ensures that more water is available for the mobility of the cement paste and you have higher workability in the concrete. You can also have a case where you want a hydrophobic surface, for example when we use a cement mortar or any other material for waterproofing. We do not want water to enter into the cement mortar and we would rather have a hydrophobic surface, therefore we can use a surfactant to make the surface reject water and ensure that water does not wet the surface. Another consequence of surface tension is capillary rise. When we have the liquid wetting the solid walls of a capillary, a thin tube or pipe, the force that is generated in the capillary rise is given here. We have now the three surface tensions that we saw before. This is the solid vapor surface tension, liquid solid surface tension and the liquid vapor surface tension. Now here what causes the force due to capillary rise is the gamma LV, the liquid vapor interface surface tension, and this creates now a circumferential force around this capillary that pulls up this liquid, and this force is given by 2 pi r, which is the circumference of the capillary multiplied by gamma LV times cos theta, where theta is this angle that you see here. This is balanced by the weight of this liquid given by pi r squared, which is the cross sectional area, h is the height and rho is the density. So this is the mass of the liquid that is balancing the circumferential force that the surface tension has created. Consequently we have this equation, h is the height of the rise of liquid in the capillary equal to 2 gamma LV cos theta by rho r, And what we see from this equation is that when r is very small, h can be very large. This is very important for us because this explains why we have rising dampness in brick and concrete structures. One might often wonder why we see dampness rising from the floor working against gravity, and the explanation is surface tension. And when we have fine pores in materials like we do in brick and concrete structures, the surface tension pulls up the water and we see dampness rising in walls and columns. We also have a very good example of capillary rise in trees. The fine capillaries that make up the fibers in the tree pull up the sap and water that feed the tree and make it survive. In concrete, the dampness rises much less because the capillaries are not as fine as that we see in nature in trees and plants. So these are some pictures of wood tissues which act as these fine capillaries and pull up the water. This is in an elm tree, and now we see here the capillaries or the tubes in the pine tree. So sap and water move up through these capillary tubes that are there in wood, and later on we will see that this is the reason why we have the microstructure that is there in wood. This makes wood anisotropic or orthotropic because all the fibers are aligned along the longitudinal direction or the direction of the growth of the tree, and this leads to a certain orthotropy of the properties in timber, and you do not have an isotropic material. Capillary rise is also important in soil. As we saw, capillary rise gives rise to a negative pressure, that is, there is a suction developed. We see here in this diagram that when we have a capillary rise, there is a pulling up of water, which we saw earlier in the case of a capillary tube, and when the pores in the soil are finer, that is, the particles are finer or closer packed, we have smaller capillaries. This gives rise to higher capillary forces and the rise is much higher. For example, if we have pores of the size of 0.0002 centimeters, we find that we can have about 730 centimeters of rise of water in this soil, whereas if it is only say 0.02 centimeters, we will have about 7 centimeters of rise. So this is important to understand that in soils with pores having small radii, you have capillary tubes forming which cause the soil water to rise above the water table. The water table could be below a surface, but due to capillary rise the water is pulled up, and this is important when we look at materials that we use for filling, say a plinth or the space below a floor. If you use very fine material, you will have smaller pores and therefore the rise of water could be higher. So this has to be either cut off by a coarse grained material at the top or some other way of cutting off the capillary rise. Otherwise a fine grained soil or fine grained filling material will give rise to higher capillary rise. Surface tension also can explain why we have forces that are generated between the walls of the capillary. We see that at the meniscus we have a force that is pulling on the sides of the capillary. This is equivalent to having a pressure that is built up to balance the surface tension, and the walls are now subjected to tensile forces. In case we do not let the walls move, we will have tensile forces pulling on these walls. If the wall is free to move, then it will deform to accommodate these tensile forces. The force that is generated or the pressure the net pressure on the liquid when we do not have any other external force applied is equal to P, which is 2 times gamma LV, which is the surface tension between the liquid and vapor, or the liquid vapor interface surface tension, times cos theta divided by r. When r is very small, that is the distance between the plates or the capillary walls is very small, you have a very high pressure being built up. And this also explains what I told you before about how an adhesive layer thickness should be as thin as possible, so that we have a high force joining the two surfaces that we want to use the adhesive to bond. P now is the difference in pressure between the inside and the outside of the liquid surface. The Young-Laplace equation gives us the relation between the pressure drop across a curved interface, now delta P in a liquid which has surface tension gamma, and the surface curvature is kappa. Surface curvature kappa is given by the sum of the inverses of the two radii of curvature R1 and R2, and now the pressure drop is given by gamma times kappa, or gamma times the sum of the inverses of the two radii. The Kelvin equation gives us the relation between the ratio of vapor pressure above the meniscus to the vapor pressure above the bulk liquid, that is where the surface is flat, as shown here. The natural log of P divided by P0, this term is now the ratio of the vapor pressure above the meniscus, the curved surface, and the flat surface or the bulk liquid, is equal to K, which is a constant depending on the properties of the interface, and the sum of the inverses of the radii of curvature. This equation gives us some explanations of interesting phenomena that we observe in materials. For example, on the left hand side we see a graph of the natural log of P divided by P0, which is the ratio of vapor pressures as a function of the radii of the pores. In pores that are close to 10 nanometers in radius or larger, evaporation of water in the pores will start as soon as the relative humidity is less than 100%. However, what we find is when the pores are smaller, we require a much larger lowering of the relative humidity for the pores to start drying. For example, when you have a pore of 5 nanometers in radius, the relative humidity has to be as low as 50% for that pore to start drying. So this means that in many materials, even though the environment is relatively dry, the pore is not completely dry, or the material does not completely dry. On the right hand side we see a diagram of the stress developed, the pore pressure developed versus the radius, and what we find is that as the pore radius becomes smaller and smaller, there is a larger force that is trying to pull on the water surface, pull the walls of the pores together until the tensile strength of the water is reached, and actually the water surface breaks because the tensile strength has been reached. And this type of force that is trying to pull on the water surface leads to contraction or shrinkage in materials when drying occurs. So as the pore is being emptied, stress develops on the meniscus, tending to pull the walls of the pores together, and this is what we observe as shrinkage in a material that is drying. So what we saw is that smaller pores do not lose water rapidly by evaporation until the partial pressure of water, that is the relative humidity, is lowered significantly, that is lowered to the equilibrium value. Pores that are less than 10 nanometers in diameter start emptying only after the relative humidity drops to below 90 or 95%. So, materials which have very tiny pores will not dry until the relative humidity drops very significantly. And also we saw that there is a stress generated as the material dries. So, as water is being removed from pores, say in a brick or concrete or even wood, we have a stress that is built up in the distribution of capillaries which exists in these materials which are porous, and this creates contraction or shrinkage of the materials. The fact that we see this lowering of the vapor pressure in a capillary indicates that the molecules now have a higher binding energy on the surface than they do in the bulk water. So, in the curved surface in the meniscus the binding energy is higher, that is why we have to create a more adverse situation for the drying to occur. Similar phenomena also affects freezing. We find that the freezing point of liquid, say water in capillaries, is reduced proportional to the size of the capillaries. Smaller the size of the capillary or the pore, lower has to be the temperature before the water freezes. Water in pores greater than 30 nanometer in diameter freeze close to the normal freezing temperature of 0 degrees Celsius. But when we have very tiny pores, pores of 0.25 nanometer, water will freeze in those pores only when the temperature drops to minus 70 degrees. That is, water in very small pores never freezes, and this is important when we look at freeze thaw damage in concrete and other materials, where we have the movement of water as the temperature is dropping. Not all the water freezes suddenly at the same temperature, but water in larger pores freezes first and then the smaller pores and so on. So, this freezing water moves and creates a lot of stresses in the capillaries which eventually lead to cracking and damage. There are other surface phenomena that are also important. One is adsorption. We saw that the solid surface has a higher energy because of the asymmetric bonding that is there for the atoms and particles on the surface. So, this higher energy leads to the attraction of foreign atoms, other materials that are outside the solid surface in as atoms or molecules, and if these have some affinity, they have some attraction for the surface, then this higher energy attracts them and adsorbs them. This effect known as adsorption is now related to this higher surface energy that we see in solids. Different molecules will adsorb with varying degrees of intensity. So, depending on the nature of the bond that forms and the type of molecule, we can have more adsorption or less. The strength of the bond also affects the degree of intensity, and all this can be expressed in terms of an energy of adsorption, just like we saw lattice energy in the bulk material. So, in this graph we see the energy of adsorption as a function of the distance of the adsorbed layer from the surface in the x axis. The negative energy indicates a positive adsorption. Lower is this well, similar to what we saw in the Condon-Morse diagram, more is the adsorption on the surface. Now, you see in this graph that there are two plots. The curve label as 1 is for chemisorption, where we also have a chemical bond forming on the surface between the adsorbed material and the host material. Physical adsorption has less of this attractive energy, the well or this drop is not as much as here. This is called physical adsorption. You just have physical phenomena and weak forces like van der Waals forces and hydrogen bonds keeping the adsorbed molecule on the surface. So, when the molecule does not react chemically with the surface, we have physical adsorption occurring through van der Waals bonds, and the minimum value of the energy of adsorption is small. We saw in the previous graph that the drop in energy was not as much as in chemical adsorption or chemisorption. If we have hydrogen bonds, as in the case of water and ammonia, we will have stronger adsorption. We saw in the second lecture that hydrogen bonds were a specific type of van der Waals bonds, and due to stronger dipoles we have stronger bonds than in the case of the van der Waals bonds, and this therefore leads to stronger adsorption. And an example of this is in clay, that clay will not lose all its adsorbed water until it is heated to 300 degrees Celsius. So, lot of energy in terms of heat is required to break the adsorption energy or to release the water that is held by adsorption by the clay surfaces. If there is a chemical reaction, then the bonding is stronger and the effect is now called chemisorption. We also know that physically adsorbed molecules can diffuse along the surface under pressure gradients. That is, if you have water adsorbed on a surface and if pressure is applied that drives the water, these adsorbed molecules instead of being released into the atmosphere will travel across the surface. Such movement occurs during creep in hydrated cement gel, as the calcium silicate hydrate gel, water moves during creep, and also in clays we have water moving along the interfaces between the clay platelets. This was discussed in a previous lecture, and this causes swelling. We have water moving into the interface between the clay platelets, giving rise to swelling in some types of clay. Finally, a phenomena that affects the behavior of many materials also based on surface property is that related to colloids. Colloids are fine materials which have very high surface areas, and we are talking here about particles with sizes less than a micron. We can have different types of colloids depending on the phases involved. Solids, liquids and gases can all exist in colloidal form and can be dispersed in either of the other phases. We can see here in this table a classification of colloids. When we have gaseous phase dispersed in a liquid, we have foam, examples being whipped cream, soapy water, foam that is used for insulation. Gas can also be dispersed in a solid, giving a solid foam. An example is air entrained concrete, foamed concrete. Then we can have liquid dispersed in gas, giving an aerosol, a spray. Liquid in liquid is an emulsion. We can have emulsified bitumens, emulsified paints, and solids can also be dispersed. When a solid is dispersed in a gas, we have smoke, and an example closer to civil engineering is in the case of silica fume or fly ash. Solid in liquid, we have examples of cement paste and clay water suspensions. This is the reason why calcium silicate hydrate is called a gel. Then we have a solid dispersion also possible, example say of thorium oxide in nickel. Let us look at the stability of colloids. Colloids agglomerate or flocculate when the attractive forces predominate. This happens often when two particles approach each other, and if there are attractive forces then they will tend to stick to each other and agglomerate or flocculate. There are several types of interactions possible. First is van der Waals forces that we have discussed earlier. We can have electrostatic attraction between charged particles of opposite signs. This is not very common, generally the particles will have the same sign or the same charge. This gives rise to electrostatic repulsion between double layers of charged particles, and then we can also have repulsion between adsorbed layers. The charge is brought in by the adsorbed material, can also lead to repulsion. We can again go back to a Condon-Morse type curve to look at the interaction forces as a function of the interparticle distance. So we have again energy on the y axis and interparticle distance on the x axis, and we have here now repulsion by the forces that we discussed earlier. We can have repulsion due to same surface charges or because of adsorption, and then we can have some attractive forces which are going to cause flocculation, say van der Waals forces and other forces. What we find is the energy diagram now has a drop, then a hump, and it comes back for a slight drop before becoming 0. This second drop is due to secondary flocculation which is reversible. The energy involved here is little, so little bit of mechanical energy can disperse the particles again. However, once this energy barrier is crossed and the material has flocculated, the colloids have flocculated causing primary flocculation, this is almost irreversible. The attractive energy is so high that the colloids are kept together as flocks or agglomerates. So what we see here is there are two minima in the curve, a shallow one called the secondary flocculation and a deeper one which is the primary flocculation. Secondary flocculation is reversible, that is by shaking the colloidal suspension or stirring we can separate the flocks. However, much greater energy is required to redisperse the colloids if primary flocculation occurs. So this is irreversible, the primary flocculation is irreversible. Or one example of flocculation in materials that we deal with is seen in clay water systems. On the left we see a single clay plate, and though this plate is now electrically neutral, we see some places which will have a certain charge and other places which will not have the same charge, and this gives rise to edge phase interactions where you have a positively charged end being attracted to a surface that is negatively charged. This gives rise to flocks. These groups of particles are called flocks, each will have a boundary and there will be a separation between the flocks until there is complete flocculation as seen here. So as we said, even though the particle, say in this case a clay particle, may be electrically neutral, there will be positive and negative charges on different parts of the surface. This may be due to the nature of the surface, the impurities and the defects that are present on different parts of the surface. Consequently, clays, because of their layered structure, form plates with residual negative charges on the surface and positive charges on the edges, which gave rise to the flocks that we saw in the diagrams in the previous slide. Now one interesting phenomena that occurs due to the surface charges is what we see in colloids or particles that are in an electrolytic solution. This is called the double layer phenomena, and we have on the left a case where we have a solid surface, we have a solid surface with a negative charge, we have an electrolyte here, the solution in which this solid particle is suspended in or dispersed in, and what the negative charges will do is attract some of the positive charges close to this surface. This is called the stern layer, and this stern layer will now move along with this solid surface as it moves within the solution or within the liquid. Away from the stern layer there is a diffuse layer which has more positive charges closer to the stern layer because of these negative charges, and this diffuses out to the normal electrolyte which has a uniform distribution of negative and positive charges. So if we look at the electrical potential as a function of the distance from this surface, we find that the surface potential is very high, then it drops off and decaying to 0 where we have the normal electrolyte, that is at the end of the diffuse layer. The electrical potential at the edge of the stern layer is called the zeta potential, and this is important because higher the zeta potential, more will be the repulsion between surfaces that have a similar charge. Now not all materials and not all combinations of materials will have a high surface potential and a high zeta potential. In this case here we have a high surface potential which leads to a relatively thin diffuse layer leading to a low zeta potential. So surface potential is high but the decay is very rapid and the zeta potential is much lower. So we see here this double layer which occurs adjacent to the charged solid particle. We have a diffuse layer which we saw here with a low electrolyte concentration. In the case of a condensed double layer we have a high electrolyte concentration or a high surface charge or surface potential. Now when ions are present in the solution, then we saw that an increased number of ions of the opposite charge occur in the vicinity of the surface. We find an increased number of ions of the opposite charge occurring near the vicinity of the surface of the particle. The charge concentration decays as the distance from the surface increases until we reach a normal distribution or a uniform distribution of ions within the solution. Some of the ions move with the solid. A layer that is closest to the surface moves along with the solid as the solid moves within the solution, and this is called the stern layer. Then there is a static part which remains in the solvent, however it has an enhanced ion distribution, and this is called the diffuse layer. Together the diffuse layer and the stern layer are called the double layer. And we also saw that the electrical potential of the stern layer, that is the zeta potential at the edge of the stern layer, is lower than the surface charge. This drop in potential is sharp while the decay in the potential is exponential in the diffuse layer, that is there is a sharp drop of electrical potential within the stern layer, whereas in the diffuse layer the decay is slower. And this double layer now decreases the energy of the system. Therefore when there is overlapping of the double layers of adjacent particles, we have two particles coming close to each other, the overlapping raises the energy of the system and consequently there is a repelling of the colloidal particles, that is the double layers formation repels the colloidal particles. So we see that here diagrammatically. In the case of A we have a condensed layer, much lower zeta potential and low overlap and the repulsion is less. But if you have a large diffuse layer, in the case of a large diffuse layer there is a high overlap and therefore there is high repulsion. And this is the basis of the design of plasticizers and super plasticizers which are meant to deflocculate cement particles. When the zeta potential of the system is higher there is better deflocculation, the cement particles remain dispersed for a longer period of time and you have higher workability. To summarize, we looked at surface properties in this lecture. we started off by looking at how surface tension develops, why liquids have different spacing of the particles on the surface and how this gives rise to tensile forces causing surface tension, and how surface tension can be used to explain capillary rise, even rising dampness. We also looked at other phenomena such as adsorption and colloidal behavior. We also saw how surfactants can modify materials to create emulsions, foams and deflocculation, and earlier we had looked at the effect of wetting and how there is research going on to create surfaces that are hydrophilic to cause more wetting and hydrophobic surfaces to cause repulsion of water from the surface. In the next lecture we will be looking at mechanical properties, we will see mechanical behavior, and from there on we will be looking more and more at properties of materials, moving away from just explanations of how the microstructure forms and how the microstructure behaves to more of engineering properties and the behavior in the engineering scale. Thank you.